So today we were supposed to have a tutorial together. No, you were supposed to have a tutorial with Freddy. Well, tomorrow afternoon, the whole tutorial will be one single Lie groups and Lie algebras tutorial. Okay?
Okay. So no
Okay.
algebra? Together with the algebra.
It will just be it will be based on Freddy's talk tomorrow. Well, and this last lecture, I guess it falls under the category of group theory, but it will basically be a short review of special relativity. Just to make sure that we all remember the basics of the Lorentz group so that you can discuss more about it with Freddy tomorrow. OK, so the main object in special relativity is our four-dimensional space-time. And we refer to events as being points in this space-time characterized by a time coordinate t and three spatial coordinates x, y, and z. We also define a space-time interval between two events. Say an event happening at t, x, y, z, and another one at t plus delta t, x plus delta x, y plus delta y, and z plus delta z. The space-time interval between the two events is defined as delta s squared equals minus delta t squared plus the three spatial squares. And this interval brings in the Minkowski metric, which is nothing but a 4x4 matrix with entries minus 1, 1, 1, and 1 in the diagonal. So that we can write delta s squared equals eta mu delta x mu delta x mu, where here I have turned the four space-time coordinates into one position vector that I call x mu. And now x0 is usually related to the time coordinate as c times t, with c being the speed of light. But in units where c equals 1, this is just t. So
if you didn't set c equals 1 before, the previous definition has.
Oh, yes, I should have had it here, yes. So let me, for completeness, let me put it in here. Yeah. OK. So Greek indices such as mu and nu usually take four values, 1, 2, and 0, 1, 2, and 3. And we usually use Latin indices for all the spatial indices. So x mu can be also written x0. xi. OK, now the question is, what kind of transformations can we make that leave this space-time interval invariant? So if we change from x mu to x prime mu, what can we do so that the delta s squared is equal to delta s prime squared? One set of possible transformations is simple translations. If we change from x mu to x mu plus a mu, where a mu is just a constant vector, then it is easy to check that this thing remains invariant. Another option is to make the equivalent of three-dimensional rotations in 4 dimensions. So I'm going to write this as rotations in our 4-dimensional space-time. And these are what you know as Lorentz transformations. So I multiply my vector x mu with the 4×4 matrix, which is a Lorentz matrix. And this takes me to x prime mu. Now, what is the condition that this matrix has to satisfy in order for this to be a symmetry as I declared? A symmetry means that delta s squared stays invariant. So let me just drop the deltas for a little while and just write that s squared equals eta mu nu x mu x nu. S prime squared equals eta mu nu x prime mu x prime mu. And this is equal to eta mu nu lambda mu rho x rho lambda nu sigma x sigma. So if I demand that s squared is invariant, these matrices have to satisfy eta mu nu lambda mu rho lambda nu sigma equals eta rho sigma. Any 4×4 matrices that satisfy this relation are said to belong to the Lorentz group. If I want to use matrix notation without explicitly writing the indices, I could have written that x goes to x prime equals lambda x. I could have written that s squared equals x transpose times eta times x. And the relation that the Lorentz matrices have to satisfy is lambda transpose eta lambda equals eta. the Minkowski matrices, the Lorentz matrices leave the Minkowski metric invariant. Questions up to here? Okay. It is easy to check that the Lorentz matrices actually form a group. If we combine two matrices, lambda 1 with lambda 2, this is equal to lambda 2 transpose, lambda 1 transpose, eta, lambda 1, lambda 2. Now we know that this is equal to the Minkowski metric. So this becomes lambda 2 transpose eta lambda 2. And this is again equal to the Minkowski metric, which means that the combination of two Lorentz transformations is again a Lorentz transformation. You can also check that associativity holds. Well, these are usual matrices, so associativity holds. We do have an inverse, which we will calculate very shortly. And the identity matrix is, as usual, the identity matrix. It is part of the Lorentz group, too. As I said, Lorentz transformations can be thought of as rotations in 4 dimensions. So we can divide them into 2 categories. Usual 3D rotations. For example, a rotation around the x-axis by an angle, say phi, will be described by a 4x4 matrix. This won't be enough. Of this form. So we have one here. That's going to be cosine p. This is cosine p.
So -1 t is the first entry.
This entry?
So unless you have time reversal as well.
No, this is not -1. I want to keep, I'm not changing the t coordinate. It stays the same. The time coordinate stays the same. And I'm only rotating y and z, basically. Yeah? Now we can also have rotations between the time coordinate and one spatial coordinate. So how should I write this? Well, these are called boosts. And in similar notation, a rotation between the time coordinate t and, say, x would have the hyperbolic cosines and sines in it. Yes? This is a rotation between t and x. Now, this is the fourth one. Okay. discrete transformations, such as reflections, are also part of the Lorentz group. For example, time reversal would just be described by a matrix -1, 1, 1, 1. And that would, again, satisfy this relation. But if we want to throw this away and keep only the ones that do not change the signs of our coordinates, then we have the proper orthogonal Lorentz group, or SO31. So this is the group, this is the Lorentz group with the extra requirement that the determinant of lambda is equal to 1, plus 1, and that the sign of lambda 0, 0 is plus 1. This is the proper orthochronous Lorentz group. And if we combine our Lorentz group along with translations, we get the full Poincaré group.
Does that include the discrete transformations or not?
Does this include, sorry?
The discrete transformations.
Yes, the full Poincaré group includes the discrete transformations as well.
So
but we can also, but if you, I'm not sure if there's a name like proper orthochronous Poincaré group, but you can also just use translations and SO31.
Let's say in special relativity, I mean, so some laws of, say, electromagnetism are invariant under some of the discrete transformations, for example.
So what is the question? If when we say Poincaré, we refer to SO31 plus translations or the whole Lorentz plus translations? I'm not sure what the... I think that the definition of the Poincaré group includes both. But yeah, the symmetries of special relativity are described by SO31 plus the translations. This is basically what we are interested in. This thing plus translations. And you can count, if you want, how many parameters this group will have. And you will find 3 for rotations, 3 for boosts, and 4 for translations. So that would be a 10-parameter group. Okay, now when we talk about 3D rotations, we understand quite well what the angle phi means there. Let's see what phi and hyperbolic sines and cosines of phi stand for in boosts. So let's just consider a boost between t and x. So I'm going to new coordinates t prime and x prime related to the original ones through cos phi minus the hyperbolic sine of phi. Okay, or if I want to be even more explicit, this means that t prime is cos phi t minus sine phi, and x is t plus cos phi x. Okay, so what does the point x prime equals 0 correspond to? For x prime to be 0, it means that sine h phi t should be equal to cos phi x, or in other words, x over t equals tan h phi. This means that in my original coordinates, the origin of this new coordinate system is moving with a velocity equals to the hyperbolic tangent of phi. So I can associate that angle that I see in the boosts with the inverse of the hyperbolic tangent of some velocity. And if I also defined gamma to be the root of 1 minus, sorry, it's 1 over the root of 1 minus v squared, then I can write this Lorentz transformation as t prime x prime equals gamma minus gamma v minus gamma v times tx. Okay, and now I can try to draw some space-time diagrams, which are very useful. So I choose to draw only the x and t axis for a specific inertial frame, and I choose to draw them as orthogonal to each other. And now how do I describe things happening in this frame? Well, an event is just a point in this diagram, right? And now, for example, a particle moving will be associated to a line in this diagram. So if I start, say, from this point, and I draw a line like this, this is some particle moving with some velocity that I can calculate from the tangent of this angle. Right? Okay, so I can draw a few lines, and you can tell me what they correspond to. Okay, so what is this particle? That's a photon. It's a massless particle moving at the speed of light. What else can I draw? what is this line? Is it a massive or a massless particle, or is it something else? It's a massive particle. And this is an, nothing is wrong with this line, right? Nothing is wrong. Okay. And what is, say, a line like this one? Exactly. That would be a tachyon. So this is something moving with a speed greater than the speed of light. Okay, finally, let me try to also draw well, a line here. So what could this correspond to?
An accelerated particle.
An accelerated particle. But again, it's an accelerated massive particle.
I think it has slightly over.
Hmm? Okay. So after this successful drawing, I can draw even more. And I can try to draw a boosted frame. So if I start from this original frame, x and t, then I can try to draw the x's, x prime and t prime that I get after making that coordinate transformation. So how do I find that? Well, if I set t prime equals 0, I get t over x equals tan h phi, or v. And if I set x prime equals 0, I get x over t equals v. Which means that my new x-axis will be somewhere here, and my new t-axis will be somewhere here. So as you perform a boost, you get this scissoring effect between your axes. I should have already said that these lines, the lines that correspond to photons, define my future and past light cones. And that any separation of events that falls inside the light cone is known as time-like, and anything that happens outside the light cones is known as a space-like thing, but I will define this better in a moment. Let me move here. And well, using those relations that t prime equals gamma times t minus vx, and x prime equals gamma minus v plus x. You can get you can get all sorts of famous results in special relativity, such as time dilation or length contraction, and you can easily check that events that happen simultaneously in one frame do not happen simultaneously in another frame. I'm guessing that you are all quite familiar with these things, right? Yeah? Okay. Okay, so let me now introduce 4 vectors. And in order to introduce 4 vectors, let me first define the tangent space at a point t, as the set of all vectors located at P. So I associate a vector space with each point in my space-time. And I can define a basis for this vector space to consist of 4 vectors, E0, E1, E2, and E3, so that every vector inside this tangent space can be written as a sum over mu v mu e mu. For example, if we take a specific curve in our space-time, this can be parameterized by how many parameters? How many parameters do I need to parameterize a curve? 1, 2, 5? 1, okay. So I take a curve and I parameterize it by 1 parameter lambda. I can define the tangent vector to be dx mu d lambda times e mu. Now, what if I make a Lorentz transformation on my coordinates? X mu goes to x prime mu equals lambda mu nu x nu. Then the tangent vector becomes x prime nu e prime nu, because once I make a coordinate transformation, the basis for my vector space will also change. And this is lambda mu nu x nu e prime nu. But the tangent vector itself should not change. The curve remains the same. The tangent vector has no reason to change. I just changed my coordinates. So, is this a question? Brenda? No? Oh, okay. So, a tangent vector itself should remain invariant. This should be equal to x mu in mu, which tells me that my basis vectors should transform in this way. Lambda mu nu E prime nu should be equal to E nu, or E prime nu should be equal to the inverse Lorentz matrix multiplying this basis. And now let's calculate the inverse of a Lorentz matrix.
Shouldn't, when the way it transform the coordinates, the vector involve also derivative in the parameter lambda?
Oh, yes, sorry. This is the x d lambda, and this is the x d lambda. X d lambda. Yes. So now it's gone there. Okay, so let's just try to find the inverse of lambda. And to do this, we also introduce the inverse metric as the same matrix eta, but with raised indices this time. And this is defined so that eta mu nu multiplying eta nu rho gives us delta mu rho. You'll see why I need this. So let me start from this relation and multiply both sides by, I will multiply both sides by eta lambda rho. So I will get eta lambda rho, eta mu nu, lambda mu rho, lambda mu sigma equals eta lambda rho, eta rho sigma, which is nothing but delta lambda sigma, which means that I can identify this bit as the inverse of this Lorentz matrix. This must be lambda, inverse lambda of lambda nu sigma. So this should be correct. Let me rewrite this here. So the inverse of a Lorentz matrix should be given by eta.
I think you have an index error.
Yes. Wait a second.
Lambda
Lambda. What did I do?
Switch sigma to lambda.
To okay. Wait. Wait a second. Lambda rho, rho mu mu nu, mu sigma. Okay, so this should be lambda nu. Yes. The inverse of lambda with indices lambda nu should multiply lambda nu sigma and give me delta lambda sigma. And if I use the metric here to raise and lower indices, I would lower the mu index here with this eta, so that would become lambda nu. And I would raise rho with eta lambda rho, so that would be lambda mu rho. And this is all I wanted to write, basically. Let me rewrite it. The inverse of a Lorentz matrix is just the transpose. Lambda. Sorry, it's not the transpose, but this is the notation that we use. Yeah. Okay. So why did I want to find this? Because I wanted to see how the basis vectors transform. So now I can write that this is equal to lambda mu nu nu. Okay. All vectors that transform with the Lorentz matrices lambda are called contravariant vectors. And they come with a raised index. On the other hand, we also have covariant vectors. They come with a lowered index. And they transform with these matrices. Now, to make this a bit more formal, I should introduce the dual space as well. So remember that always the dual to a vector space is a set of operators. So I'm talking about the dual space, dual tangent space. So the basis of this space, if I denote the basis vectors by theta naught, theta 1, theta 2, and theta 3, we should imagine them as acting on the basis vectors of the tangent space. And by definition, theta I of Ej should be equal, or let me use theta mu of E nu should be equal to delta mu nu. And any dual vector, let's call it omega, should be written. We should be able to expand it in this basis. And then this thing belongs, if this is a dual vector, it belongs to the dual tangent space. So we should think of it as something acting on the vectors of our tangent space. And the way that omega acts on V is defined by this relation. This is omega mu theta mu acting on V nu E nu. This is a linear operator, so I can pull V nu out of the brackets. And then I get omega mu V nu delta mu nu, or omega mu v mu. And this is our usual scalar product. So dual vectors take us from vectors in our tangent space to scalar products, which are just real numbers. Does this make sense? Yeah? Of course, the dual space of the dual space is the space itself. So you can also think of V acting on omega as exactly the same thing. And in the end, we just drop the vector notation. We forget about the basis, and we just use omega mu and v mu whenever we refer to vectors or dual vectors.
I have one question. Here in this scalar product, the temporal part and the space part will have the same sign.
No, because I should have defined this better. Here, I'm assuming everywhere. Well, if you write the indices in this way, yes, this is going to be omega 0, v0 plus omega 1, v1 plus blah, 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 blah. But if you want to raise or lower indices, you should always, can you see if I write here? No, OK. OK, so if you want to raise or lower indices, this is going to be minus omega 0 v0, for example, plus omega 1 v1, or minus omega 0 raised v0 plus v1 omega 1, and so on. OK, and let me write this here too. It's easy to check that in the same way, the components of the dual vector transform with the transpose Lorentz matrix, lambda mu mu omega nu. OK, a simple example of a dual vector is the gradient. So say we have some scalar function over space-time coordinates. Let's call it f of x. Then we can define the gradient df equals the partial derivatives of f with respect to our coordinates. Sorry, theta mu. Times the basis vectors in the dual space. And let's see how this thing transforms under Lorentz transformations. So what happens to df dx mu when we go into a different coordinate system? It becomes df dx prime mu, which can be written df dx nu dx nu dx prime mu. And I'm sure you know this already, but I want to stress that here I am summing over the indices mu. OK. Now, how much is this? well, I don't have time to do it now, but you can easily check that this is just df dx mu lambda mu nu. So the gradient, which we can also write, this part, I can also write it d mu f, will go into lambda mu nu d mu f. So indeed, the components of this vector that belongs in the dual vector space transform under Lorentz transformations following this rule. Now, we can generalize our vectors to tensors. And we can define tensors of rank, say, KL. So a tensor of rank KL will be an object belonging to the vector space which is the product of the tangent space K times the dual tangent space L times. So a tensor of rank KL is, sorry, I'm not sure I said it right before. A tensor of rank KL is a map from this vector space to R. It will be written as, let's say I call this object T. Then this will have K raised indices. How should I label this? mu1 up to mu k. And L lowered indices. So it will have K times L components multiplying the basis for this vector space, which is nothing but E, how should I write this? E mu1, E mu2 up to E mu k, and then theta mu1, theta mu1 up to theta mu L. But usually when we talk about tensors in special or general relativity, we forget that they are really the map from this vector space to real numbers, and we refer to tensors as just the components of these tensors.
Should it be LTP times TP, TP, and K, TP star, TP star?
Wait a second. What is... no, I'm following Son Carroll's conventions. And this is, for example, the metric will be a rank 0, 2 tensor.
But you can't insert K vectors.
I think that's from two vectors.
If the metric is less than, then it should be as latent as.
There should be a.
If the metric
Sorry. One at a time.
so if the metric is 0-2 tensor,
Uh-huh.
so it eats two vectors, so two normal vectors, not two dual vectors, which means it should be.
Oh, yes.
the other way around.
You're right. Yes. You're right. Yes. Yes, but this is correct. Okay. Okay, and since we know how to transform each of the mu and theta mu's, and we want the tensor T to be invariant under Lorentz transformations, we also know how to transform all the components of the tensor. Each raised component will transform with lambda, and each lower component will transform with the inverse lambda. So under a Lorentz transformation, T mu1, mu k, mu1, mu l will go to lambda mu1, rho 1, lambda mu k, rho k, and then lambda mu 1, sigma 1, lambda mu l, sigma l, times T, sigma 1, sigma l, rho 1, rho k. Okay, so as I said, for example, the metric is a 0-2 tensor, which means precisely that it acts on two vectors belonging to TP. Eta will act on the vectors v and u, and we'll take them to eta mu nu, v mu, u nu. And I can also define v squared to be eta mu nu, v mu, v nu. And if v squared is greater than 0, we say that the vector v is space-like. If it is less than 0, it is time-like. And if it is 0, this is a light-like or null vector. Okay, time is running out. So last thing I can say about tensors is that once you start contracting indices, you lower the rank of the tensors. So if you start from a tensor of rank KL and you contract one lowered and one raised index, then you go into a tensor of rank k minus 1, L minus 1. And this is where we have to stop. So questions? No? I thought I saw a hand. OK, other questions? OK, complex analysis then.